Okay, one of the things that we haven't really talked about in this class so far is nonparametric equivalence of the parametric tests. So what do I mean when I'm talking about nonparametric tests? So when we think about the parametric tests that we've been running, things like t-tests and an analysis of variance, we've talked about the assumptions that are necessary to be met in order for us to employ that particular test and reach a conclusion that is correct, i.e., an answer that's not going to have a very high type 1 error rate, concluding that two things are different when in actuality they're not. And these assumptions we've been over a gajillion times before. Basically, the data collected are independent. The data collected are collected randomly. The distribution of sample means is normally distributed, and sample variances are homogeneous. The fancy pants name for this is homoscedasticity. That's what it means to have homogeneous variances, or you can just say homogeneity of variances. It doesn't really matter to me one way or another. So here we have the normal assumptions, but when these assumptions are not met, people often default to nonparametric alternatives. In many cases, these methods involving converting all the data to ranks, so regardless of treatment, so it just puts all of the data in one big pool, and then ranks them from smallest to largest, and then reapportions those data back into their treatments, and then testing to see if those ranks by treatment are actually different. The assumptions of these nonparametric tests are that the data collected are independent and they are collected randomly, but the place where you get into trouble or you get freed up is that the populations are identical except for a possible difference in location, i.e. the mean or the medians are different. Note that these are less restrictive than the parametric test, but they're not super less restrictive because the two distributions have to have the same shape. So if you have, and I've alluded to this in class, and I'll just draw here in a minute. So if you have two distributions, one distribution is skewed positively and another distribution is skewed negatively, these two distributions, they're not only not normal, but they're also not the same shape. In a similar way, you could have two distributions. One that has a very narrow variance, a very narrow distribution, and another one which has a very wide distribution. Once again, these may both be normal, but they have heterogeneous variances. And in both cases, these are not amenable to parametric methods, nor are they really amenable to non-parametric methods because they're not identical except for a possible difference in location. Identical, but with a difference in location, would be two distributions that look like this. Where these two distributions are approximately the same, but their midpoints, whether it's the mean or the median, are just at different places on the x-axis. And so if you have heterogeneous variances, which is a super common violation of the assumption of non-parametric tests aren't met either. And when this happens, non-parametric methods aren't any better than parametric methods, and in many cases, the parametric method will still have more statistical power. So the equivalent non-parametric methods for the methods that we have been using is the Mann-Whitney U-test, which is analogous to a two-sample t-test, and the Kruskal-Wallis test, which is analogous to ANOVA. Both of these rely on the sums of the ranks weighted by the sample size to make a determination as to whether or not these things differ in location. And if the rank sum is high or low for a particular sample size, chances are that the original data were higher or lower for that sample. So we have the Kruskal-Wallis test. This is just a section that I pulled out of a nonparametric statistics book. It is in my office. So it says here, an intuitively appealing test statistic is one that determines whether sums of the ranks are sufficiently disparate that they are not likely to have been derived from samples from identical populations, leading to a rejection of the null hypothesis, whether they are close in magnitude that we cannot discredit the hypothesis of identical population distributions. So this is a weighted sum of the squared deviations of the ranks from the expected sum of squares. And this is how you would calculate it. You would basically, for each sample, you would get the sum of the ranks after having ranked all of them in one big pool. You would subtract from that the sample size of that sample times the grand sample size, which in the case of the P data set would be 50 plus 1 divided by 2. You would take that whole thing and square it, and then you would multiply it times the reciprocal of the sample size, and then multiply it times this constant here in the front, which is based once again on the total sample size. You could use this equation, or you could also use this other equation that is a little more mathematically tractable, which is just the sum of the squared ranks divided by n multiplied times 12 over big N times n plus 1, and then subtract 3 times n plus 1 from that. So we have worked with the P's data set, and so somewhere in your files you should have the P's example, and this is my version of the P's analysis in my Excel file. I've got control, 2% glucose, 2% fructose, 1% glucose and fructose, and 2% sucrose. These are calculating the means, the sum squares within. These are sum squares among. And down here at the bottom is a ANOVA table. And we've now worked through this a number of times. So what I've just done in this thing is I've basically copied over the raw data. So here we have two columns over here where we have control 75, control 67, 75, 67, 70, 75. Control 2% glucose, 2% fructose, a 1-to-1 mixture, and a 2% sucrose. Then I copied these into another couple of columns, and then I sorted them from the smallest growth to the largest growth. And then I went down and I assigned ranks to them. And since there are 50 observations, we have 50 ranks. But then what you'll notice is that in some cases there are ties. So in this case, 56 appears 3 different times. So what you do with that is you can highlight the ranks, and you see 1 and 2 and 3, that all adds up to 6. Down here, in this corner here, in this part of your Excel spreadsheet, it'll tell you that you have a sum of 6, you have 3 observations, so the average is 2. You apply that average to each of those tied things. Here we have 57 that appears 1, 2, 3, 4, 5, 6, 7 times. We don't actually have to count those up. We can just highlight those ranks of all the 57s. It gives you the sum, it gives you the count, and it gives you the average. You place those averages in there. Once you have done that, you have the treatments that are associated with those sums. You can then resort those and put them back in order by treatment. Once you have those treatments, you can get the sum of the ranks. And then, once you have that, you can get those ranks squared. And then this is the sum of the ranks squared divided by the sample size, which goes into this equation right here, the sum of the squared ranks divided by the sample size. And then down here at the bottom, I've basically calculated what 12 divided by 50 times 51 is, which is this first part right here. And then I have 3 times 51, which is 153. And so then this is the sum of all of these squared ranks. And so that ended up being 38.11. I also calculated it the other way by basically putting in an equation up here at the top that calculates this part of this equation up here. When we sum all of that up, that figure appears right here. Multiply that times the first part of this equation, which is the same as the first part of that equation, and it gives you the same result. We then take that result and we evaluate it at a chi-square using the chi-square table. And so we have 4 degrees of freedom because we had 5 treatments. We have a chi-square value of 38.11, and when we go to Daniel Soper's website and look up what the p-value is that is associated with that, we get a p of basically 1 times 10 to the negative 7th, and you'll see that that p-value is not very far off from 2 times 10 to the minus 6th. So it's a very low p-value. It's basically telling you the same thing, except that in this case, it's doing it with ranked data rather than unranked data. And so this is how you would run a Kruskal-Wallis test. In the R script, if you want to test this in R, you can do this by just basically typing Kruskal.test. What's the variable that you're wanting to test differences in, and what is the treatment that you are doing, and tell it the data frame that you are doing that in, and it will give you an answer. In this case, the chi-square is slightly off of what we calculated, and I haven't figured out exactly why that is the case, but once again, it's giving us a very similar result as what we had before. And so either of these ways of going about doing things is the correct way. You can just add those 2 lines to your R script in the P's analysis R script, and it will rerun the data using a non-parametric method. So once again, all of these non-parametric methods make the assumption that you don't have to have normality, but you have to have distributions that are similar enough to one another such that they only differ in either the mean or the median, but the shape of the distribution should be the same. So some of you are probably working your way through the Gecko data file, and one of the things that you're finding when you look at the Gecko data file is you're finding that the data are not normal and the distributions are not homogeneous in terms of their variances. And so what I did was I just plotted the data, as you can see here, such that we have summer Galveston, summer Oklahoma City, winter Galveston, winter Oklahoma City. I've plotted the means, but I've also plotted the 95% confidence intervals, and you see that in summer Galveston, the data are much more compact, and in summer Oklahoma City, the data are much more compact. In the winter, in both populations, the data are more variable. And the other thing that you'll notice is that in some populations, you have some outliers that don't necessarily appear in other populations. Now, in both of these cases, one could argue that we have a huge sample size, 50s and 60s here, 20s and 30s down here, if I'm recalling correctly, such that it shouldn't really matter if we have a lack of normality in the data, because we're testing means. We can be assured that the central limit theorem will kick in and solve the normality issue. But as I've talked to you before about, normality is really the least important of these things. What is really bothersome is the variance. Now, Tom emailed me with a question about this, and my answer to him was basically that even though there are some outliers here, in all cases, the means are much further away from one another than the differences in the variances are. So if we go back to I have a temp data file somewhere here on my computer. Let me make sure that I've loaded the data frame into here. When we go down and we get a summary of the analysis, oh, that's not right. Something is wrong here. Let me go and find the data file real quick here, or the correct R script. That was not the correct R script. That was the R script that I was working on some time ago. Hopefully this is the right R script. So when I go down here and get a plot of this, what we'll see is when we look at the confidence intervals here, the differences between the means when there are differences are quite large, 5 degrees and 11 degrees here, whereas the confidence intervals are all really, really low. And so I'm not terribly worried about differences in variance because the variance issues that are here are really small relative to the differences that we see among the means. And so if I were analyzing these data, I would probably dismiss the fact, even though we don't have an overall homogeneity of variances, the differences between the means are so large when they are different that minor differences in variance aren't going to negatively affect the general conclusion at the end of all of this. And so that would be what I would advise you to do. But there's nothing that says that you can't go and test using Kruskal-Wallis. Just once again know that because this one has a larger variance, it is not the same shape as this one over here because this one is broader than this one. So they don't differ only in location, they differ in location and shape potentially. And so anyway, we'll talk about this on Monday. And if you have any questions about how to go out doing this, we can address those on Monday. And then on Wednesday, we'll start talking about two-way analysis of variance so that we can start moving on and progressing through the remainder of the topics in the course. And I'll talk to you guys on Monday.